Hello, everyone, and thank you so much for having me. So today we're going to talk about artificial neural networks, and we're going to make it simple, broad view, without going into too much mathematical details, so that you guys would feel more comfortable about it, so that you'll be able to explain in general terms how a neural network works, why we need neural networks, and so on and so forth. So as for the contents of this talk, so first we're going to talk about the biological motivation of artificial neural networks. Remember that even though they do remind us of actual biological neural networks, they're not really in their current form, in their common form, inspired by biological neural networks. There are major differences between the two realms. And people tend to, and by people I mean the scientists in the community, they tend to focus on two main branches of this particular realm of machine learning. So one branch would always try to sort of breach the gap between the biological and technological, or say machine learning worlds, and make artificial neural networks as similar as possible to actual biological neural networks, whereas the other branch would just try to make artificial neural nets that work beautifully. So next, we're going to talk about the big picture of ANNs and the motivation behind them. Also, later on, we're going to point out a very important fact, and it's that an ANN, an artificial neural network, is nothing but an approximator. And what does it approximate? It approximates the truth that we don't know, right? So it's like, there is this truth that we want to learn. We don't know what it is, but we want to learn that truth. We want to converge that truth. An amazing topic, really great stuff. Now, next we're going to talk about the idea of an error function, which tells us how poorly or how well are we doing. So is the model predicting what it's supposed to predict correctly or poorly, the wrong way? So we need to be able to numerically sort of measure this. Next, we're going to talk about the general training cycle of an artificial neural network, and finally, we're going to just touch on and just introduce the idea of gradients and how this famous algorithm called the backpropagation algorithm and gradients are used by ANNs to train them. And by training them, I mean by tuning the little parameters that they have inside their body. Now, in terms of biological motivation, so we do have biological neural networks in our body. Now, ANNs are inspired by biological learning systems. So a BLS is a massive interconnection of neurons, and it has over nearly 10 to the power 11 neurons, each of which is on average connected to 10 to the 4 other neurons. The big picture of an ANN. So imagine you've got this big blob that, let's call it ANN. Let's say it's just a black box. We don't care what it is. We don't care what's inside of it. Let's say the job is to classify an image, a brain MRI image, into either healthy or tumor, meaning that the patient has a tumor in their brain MRI image, or they have no tumor, meaning that they're healthy. And so an image like that comes in, and that's, as you can see, it's a healthy brain image, right? So that will be classified as healthy, whereas this image on the top right side of it, you see that there's a little sort of white mass, which is a tumor. So your ANN should be able to classify that as a tumor, right? Same story here, it's a healthy image, and now this one is a, let's call it tumorous image. So that's the big picture. That's the type of thing that you'd expect from an ANN to do. And this is called a binary classification. Now, let's go a little bit deeper into the biological motivation. So what you see here is a basic nervous cell, or you can call it a neuron, right? This is a biological neuron, the basic element of a neural system or a nervous system. Now, you have the nucleus at the very core of it. You've got these dendrites that sort of search for the presence of chemicals around it. So when the neuron senses the presence of a certain chemical, like certain chemical type material around it, what it does is it sort of lets the nucleus know that, okay, there's this presence around me. I can feel these chemicals surrounding me, right? And then if that presence is stronger than a certain threshold, the nucleus actually starts, let's call it firing, right? So this electrical signal starts, gets generated, and then it starts to travel through this sort of little line that you can see in the middle. That sort of branch is called an axon. So this electrical signal travels through the axon. So remember, we have that thresholding happening before we decide whether we're going to generate this electrical signal or not. So after it travels through the axon, it reaches the axon terminals, where again this neuron sort of secretes these neurochemicals into its environment, and again those neurochemicals travel around towards the neighboring neuron. Again, the dendrites of the neighboring neuron would start to feel certain presence of certain chemicals, and again they let the nucleus of that neuron know that there is something happening around us, and again, and so on and so forth. So one neuron is connected to the other, and that's how a signal travels throughout a nervous system. Now, some sort of a similar design to a neuron is something that we call a perceptron in the realm of artificial neural networks. You might be interested to know that this is actually the very first artificial neuron. So over here, you see x1, x2, and xn. So this is sort of a vector of input data, right? So you can think of them as neurochemicals. And each one of these input data are sort of combined by these things, W1, W2, all the way to Wn, which are called the weights, right? So a linear combination of all of them, you can see here over next to the sigma sign. So Wi, Xi, multiplied together and then summed up across all of the inputs. So this is what we call a linear combination, using the parameters or the weights of this perceptron. Now, the result of this linear combination, which is nothing but a scalar, is going to travel into this little sort of circle over here that you see. That is called the thresholding function. In particular, we call that a step function, right? So if this sigma Wi Xi is bigger than 0, meaning that it's positive, the output of this thresholding unit of this step function is going to be 1. Now, if it's 0 or less than 0, the output of that threshold function is going to be -1, right? So this step function is always going to generate either 1 or -1, right? Depending on the magnitude of this linear combination of Wi Xi. Now, if we use something like this in the task that we just talked about for binary, classification of brain MRI images, so what you do is you would like to tune these W's in such a way, these W1, W2, Wn, in such a way that this magnitude, the magnitude of this linear combination, is gonna be is gonna change in such a way that the perceptron is gonna would generate +1, for example, for all the healthy images, and -1 for all the tumor images, or the other way around, doesn't matter. But it could discern between the two classes by generating +1 for one class examples and -1 for the other class examples. So if the perceptron learns its weights, those weights, in such a way that it could generate the correct output corresponding to different classes, then you can say that, okay, the machine has learned to do that task. And by learning, again, we mean tuning its parameters. Remember, this is just a simple perceptron, right? This is the simplest type of neural network, artificial neural network they could get. Now, when we talk about artificial neural networks nowadays, we're talking millions of parameters, millions of weights, millions of layers and neurons, and sort of intertwined into one another. I mean, it goes mad, right? But in all of them, when you talk about training an artificial neural network, it means I should change my weights in such a way that I would produce the correct output. I would predict whatever it is that I want to predict correctly, right? So that is what we mean by training an artificial neural network. Now, if you think about on the left-hand side, a sort of intertwined, branches of neurons and axons all together in a biological system, the corresponding thing to that in the realm of artificial neural network is something that you see on the right-hand side. So again, you've got your input layer, which is the very first layer of your ANN. That's where the data comes in. That's sort of like the neurochemicals are traveling in this liquid in the body, and they just sort of travel around and get close to the dendrites of the first layer here, a layer of neurons, and we call this a hidden layer, right? So a hidden layer, this is hidden layer number 1, and next you have hidden layer number 2, and then hidden layer number 3, and eventually after all of these layers, you get the final layer, which is your output layer, which has 4 outputs, right? Now, you notice that these layers are fully connected, meaning that, for example, the first neuron in hidden layer number 1 is connected to all of the neurons in hidden layer number 2. So this is what you call a fully connected multi-layer perceptron, or MLP, or a fully connected ANN, you could also call that. And we have 4 outputs, so you can think of this as, okay, a sort of a neural network that is going to learn to predict, to discern between 4 different classes of things, right? For example, given the stock market information, which is going to be your input data, can I predict the level of inflation? So it's going to be low, medium, high, very high, something like that, right? So you'll have 4 classes. So the job of the neural network is to tune all of its weights, of which you have so many in this network. Remember, each edge has a weight. Can I tune the weights in such a way that, given the market information, I can predict the correct status of inflation of all the 4 classes? That's called learning. And the reason we call those layers hidden layers is simply because they're inside the network. There are these levels of abstraction between the input data and the output data. The way your input data changes and gets manipulated with, through all of these neurons and weights, you'll have so many mathematical operations between the input layer and the final output layer that's going to be the predicted class. So many mathematical things happen in the middle that they would transform your input data into different weird things, right? Because of that, we call these hidden layers, right? So we don't know what's really happening inside of it, even though, yeah, we designed them, but we can't. There are efforts to that people try to understand what's really happening in a deep neural network, and there are, methods to try to, that people try to create interpretation, explanation out of these artificial neural nets. But then again, to this day, deep neural networks remain to be sort of not as much interpretable and explainable as one would like them to be, right? So that's the reason we call them hidden layers, because they're just different levels of abstraction and abstraction of the input data that you feed into the network. So many things happen to the neural network, to the input data, and each one of these layers until you could have a single freaking prediction, right? Now, let's talk a little bit more about ANNs as to what they're actually trying to do, regardless of the type of ANN that you're working with. So you've got these cute cats, right? Now, ANNs, what they do, they try to learn the truth, approximate the truth. Now, let me tell you something about the truth. Let's say we want to ask this truth function to classify these images, right? So by function, I mean You give it an input and it spits out an output. That's all a function is, right? So if I gave all of these four cute kitty pictures to, to the truth function f, and ask the function, what are these? It just with no problem says they're cats. Now, if we had weird pictures, if we sort of try to even deceive the truth, so you got these funny cat that with some sort of in a furrow, outfit. You've got like half a face of a cat that's hiding in a box. You've got this weird looking cat, looks like a sock that is turned inside out. And you've got this other cat during the pandemic wearing a mask. So the truth doesn't care, right? You do whatever you want. The truth function will still say these are cats, right? So that's the beauty of the truth. It knows it all, right? And ANN tries to approximate that function. And that's what we want to take from this slide. Now, what sucks is that we don't know what f is. We don't know what the truth is. We cannot describe the truth, right? But what we can do, we can try to approximate the truth because we have so much data, right? At least we hope to have so much data. Now, the type of prediction that you could expect from an artificial neural network is this. For example, if the input data is an image, the prediction could be, okay, with probability of 70%, I'm going to say that this is an image of a cat, and 30% it is a dog. Now, let's say you given the information related to the oil price per barrel, you put all of this input data into an artificial neural network, and it can produce the price of the oil, say in the next month or next week. So here it's literally producing some sort of real valued number for you, right? And eventually you might actually input the data related to cars, right? The power of the engine, number of seats, the color, the model, and then it can predict how many cars you're going to sell in your garage, right? So here you've got a natural number. This is just a decimal, like an integer, basically, right? So these are the types of predictions that you could expect from an ANN. Now, these are not the only types, okay? So these are just very common ones, let's say, for our discussion. So ANN approximates the truth, right? Now, the other thing that we want to talk about is, okay, let's say your ANN is predicting, it's generating all of these different types of predictions that we talked about in the previous slide. Now, there must be a way, surely, for us to be able to, assess the quality of that prediction. Are we screwing up or are we doing a good job? So let's say this cat comes in and the prediction is that it's a cat. And you can look at the truth because we assume that we have the truth in this example. And the truth says, well, yeah, it is a cat, right? And because our prediction and the truth are both identical, the error is 0, right? Now, all of a sudden, you might come across a weird cat, right? Something that you have never seen before. Something like this. I mean, oh my God, that's one scary cat, right? What the hell is it doing with its tongue? I don't know. Whatever it is. I mean, I get nervous looking at it, to be honest with you. Anyway, if you ask the ANN, it might just say this is the devil's incarnate, right? I mean, there's no way in hell that it's a cat. But then when you consult with the truth says, well, I know it's a weird looking cat, but it's a cat. In this case, the difference between your prediction and the truth is just mind-bogglingly, high, right? So it's a huge number, right? So after you can numerically, quantitatively measure the error of your prediction, you have to let your ANN know. You have to say, okay, you did a good job, all great, or you did a terrible job. You need to adapt. You need to tune yourself. You need to learn from your mistakes, right? And that is when we do this thing called, let's backpropagate this knowledge back to the artificial neural network. We backpropagate this knowledge, right? You notice that I'm putting an accent on, on the word backpropagate, because that's a key word that we're going to go back to. We're going to get back to in the some of the future slides, right? So this is why we need the error. We use the error to measure the quality of our performance, and then we use that error to let the artificial neural network know, look, you have to change the weights inside you. You have to increase that weight. You have to decrease that weight. You have to tune yourself so that with the next image of a cat, you'll do a better job. So that hopefully the next time you see something as weird looking as this, God knows what it is, this cat, I want you to change your weights in such a way that in a similar situation, you're not gonna predict something weird. You still recognize this thing as a cat, okay? Right. Now, let's talk about the training cycle of an artificial neural network. So when we talk about training a neural network, what we typically have is something that is called a training set. You've got so many data points in that training set, and you want to use those data points to train an artificial neural network, right? There are many different ways of using, your training set to train an artificial neural network. I'm going to talk about one of the methods, but if you get this idea, you can easily generalize that to different methods of training an artificial neural network and different ways of utilizing your training set, right? So humor me for a second. Now, this is your ANN. It is stupid. It has nothing in its repository. It has no knowledge. All it has is a bunch of parameters, right? That it has just randomly initialized. I mean, you have just random numbers for those weights out of nowhere. I mean, it has no idea about the world around it. Now, here is where we inject some knowledge into it. So the first data point, x1, comes in, and then does some weird mathematical manipulation to it, and then eventually spits out the first prediction about it. It can be anything. Okay, it could be oil price, it could be the number of cars sold, it could be the class of an image, whatever have you, irrelevant, right? But it just produces this prediction. And then you pass the prediction 1, which is the prediction for the first data point, and the truth about the first data point. Let's denote it with T1, truth, right? So this is what I predicted, this is what the truth is. Mr. Error function, can you compute how much I've screwed up, right? So the error function computes how much you've screwed up. It could be high, it could be low, and then you backpropagate the knowledge that you get out of this error back into your artificial neural network, and then you see this little robot with walking and sort of thinking about with that wheel, like it's thinking how I should change all of my parameters to do better next time. So this is where the neural network changes its parameters in such a way that it could hopefully do better with the next input data. Now, the next input data comes in, x2. So the second prediction, p2, is generated, and then the prediction p2 and the truth about the second data point, which is t2, these two are passed into our error function. And then you compute how much you've screwed up or how well you've done. Again, you backpropagate this knowledge back into the neural network, and then it again ponders, it again broods upon how it's done, and it sort of tunes its parameters. So these keeps happening until you finish all of the training data in your training set, right? So that is the cycle of training an artificial neural network. With every input data, you can measure how well you've done, and you can update the parameters of your artificial neural network. Again, as a side note, this is not the only way of doing this, okay? But this is the soul of it, the spirit of it. If you understand this, you'll be grand, as the Irish would say. You'll be grand. I mean that you'll be okay in understanding the other methods, right? Now, when you go through all of the data points in your training set once, that is called one epoch in artificial neural networks terms. So imagine you're in the bar, and then this friend of yours is bragging about their artificial neural network, and then they say, yeah, I set up the total number of epochs to 50. And then it looks at you, in a some sort of a know-it-all way as a, yeah, you have no idea what I'm talking about. Then you could just say, well, I know, I actually know what you mean by an epoch. So why didn't you increase the number of epochs? And then he says, you know what an epoch is, and then you say yes. when you say you have trained your artificial neural network for 10 epochs, it means you went through the entire training set 10 times, right? So you visited your training set 10 times and you passed all of that data through your neural network 10 times, right? And the main reason for this is because, as the old saying goes, practice makes perfect, right? Now, let's sort of touch on the idea of backpropagation algorithm. Now, it is a method of letting each parameter in your artificial neural network, which are the weights of your artificial neural network, you want to let them know how much should they increase or decrease so that the error will decrease, right? So this is called training, right? So you backpropagate the knowledge that you get, after computing the error. You backpropagate that knowledge throughout the entire network. Doesn't matter how many parameters you have, you'll talk to each and every one of them and you let them know how should they change, right? Now, what do we backpropagate? So I kept saying, okay, we backpropagate the knowledge. That knowledge has a name in artificial neural networks, and that is called the gradients. Now, more specifically, the gradients of our error function with respect to each and every parameter in our artificial neural network. Now, in other words, if I say I compute the gradient of my error with respect to W1, by the way, the result of that is just a simple number. What that number shows, it shows how sensitive is this error function with respect to slight change in W1, right? So how much am I gonna bother this error? If I change a little bit, is the error gonna jump madly high, or is it just gonna plummet down with a single change in my value, right? So how much of a say do I have in the final performance of my model? So these gradients, so after you produce a prediction, you let all of the parameters know in your neural network where they're standing, how important they are in the ultimate prediction. And that knowledge, my friends, that gradient is going to be used by the neural network to know how to update each and every one of those parameters or weights, right? So in other words, the error function, let's denote it with E, and then W, let's call it let's say it's a parameter. It's one parameter of millions. Now, the error asks this question: how much will I change if you change a little bit, right? And then the weight says, well, no clue. I have no idea. Can you tell me? And then that is where the error computes its gradient with respect to that W, right? So the partial derivative of error with respect to W is what we call a gradient. And then the W says, great, now I know how to change. Now, of course, it is mathematically driven. I don't want to go into the details of that because that's not the purpose of this talk, okay? This is just to give you a general idea, give you the good keywords that you might be able to use and go and search the bits and pieces that interest you the most. But this is the idea. We backpropagate the gradients, okay? And then the weights will know how to change, knowing those gradients. Okay, great. So I think with that final slide, we've come to the final, the end of our talk. So if you found this, useful, we've got so many interesting posts on mldon.com. Again, feel free to subscribe to our YouTube channel, mldon, and also you can follow us on Twitter and LinkedIn and the Facebook of mldon. And thank you so much for giving me the opportunity to talk to the people at Insight and share some interesting stories about artificial neural networks. It was certainly enjoyable for myself, and I hope that you guys have enjoyed that too.